In this question, a scientist is investigating the reversible dissolution reaction of silver sulfate, Ag2SO4, at 20 degrees C. Remember, dissolution just means dissolving. Our first step is filling in the gaps to balance the equation. So we have Ag2SO4, and we can see that it's creating Ag plus ions and SO4 2 minus ions. Since we have Ag2SO4, we're going to be creating 2 Ag plus ions and 1 SO4 2 minus ion for every formula unit of Ag2SO4 that dissolves. So in our equation, we're going to have 2 Ag plus and 1 SO4 2 minus. We're also told KSP, the solubility product constant, or in other words, the equilibrium constant for the dissolution reaction, is 6.76 times 10 to the negative 5. Our next step is finding an expression for the reaction solubility quotient, QSP, for this reaction in terms of the concentrations of the ions. This works exactly the same as finding the reaction quotient, and that works exactly the same way as finding the expression for the equilibrium constant. So to find our QSP, on the top of our fraction, we're going to have our reactants. Remember, only aqueous or gas substances are included in the equilibrium constant or the reaction quotient. So here we have Ag plus AQ, so that can be included in our equation, and we've got a coefficient of 2. So that means we've got the concentration of Ag plus, and it's going to be to the power of 2. Then we've got SO4 2 minus. Again, it's aqueous, so it's going to be in our equation, and we've got a coefficient of 1. So we're going to have the concentration of SO4 2 minus to the power of 1. Remember, to the power of 1 is just the same as the thing itself. On the bottom of our fraction, we've got Ag2SO4, our reactant, but it's a solid. Solids are not included in our equilibrium constant or reaction quotient equations. So we don't have anything on the bottom. That's just going to be 1. And dividing by 1 is the same as just the thing itself. So there's our expression for QSP. We've got Ag plus squared and SO4 2 minus. Remember, Q compared with K have the same equation, but K only applies at equilibrium, whereas Q applies at any time. Next, we're told a scientist mixed together 0.68 litres of 4.58 molar silver nitrate solution and 0.320 litres of 2.82 molar magnesium sulfate solution. First, we have to figure out what will our concentrations of Ag plus and SO4 2 minus be in the solution mixture. Okay, for silver nitrate, which is AgNO3, we have 0.680 litres of a 4.58 molar solution. For magnesium sulfate, we have 0.320 litres of a 2.82 molar solution. So when we mix these together, the total volume is going to be 0.680 plus 0.320, which gives us a total volume of 1 litre. So it's almost like our solutions are being diluted to 1 litre total volume. So let's use our dilution equation. Here's our solutions reference sheet, and here's our dilution equation. M1V1 is equal to M2V2. So the molarity of the solution initially times the volume of the solution initially is equal to the molarity of the solution at the end times the volume of the solution at the end. So if we're trying to find our final molarity, M2, we're going to divide by V2 on both sides, and we're going to be doing the molarity of the solution at the beginning times the volume at the beginning divided by the volume at the end. So our final molarity for AgNO3 is going to be 4.58, which is our initial molarity, times our initial volume, which was 0.680, divided by our final volume, which is 1 litre. That's going to get us a final molarity of 3.11 molar. For MgSO4, we have an initial molarity of 2.82 multiplied by an initial volume of 0.320 divided by a total volume of 1 litre. If we put that into our calculator, we're going to get a final molarity for MgSO4 of 0.902 molar. Let's fill those in over here to make sure we got those correct. Awesome. So we know our initial concentrations of silver ions and sulfate ions. We also know our expression for QSP. So we can go ahead and calculate QSP at the beginning of the experiment using those initial concentrations. So let's go ahead and put those numbers into our equation here. So for Ag plus, our concentration was 3.11, and that's squared, multiplied by for sulfate, which was 0.902. If we put that into our calculator, we're going to get an answer of 8.75 for our reaction solubility quotient, QSP. So we now have our QSP value at the start of the experiment is 8.74. We also know our KSP value is 6.76 times 10 to the negative 5. That was provided under the equation in the question. And we can now use QSP and KSP in the same way that we've used Q and K to figure out what's going to happen next. Now in this example, Q is 8.75 and KSP is 6.76 times 10 to the negative 5. So Q is way bigger than K. So we can answer this question at the start of the experiment, which is greater, the reaction solubility quotient, QSP, or the solubility product constant, KSP? The answer is that Q, the quotient, is way bigger than K, the constant. Now Q changes throughout our experiment, and if the reaction is left to run its course, eventually Q will equal K when the substance is at equilibrium. So Q is going to need to decrease until it reaches K. In order for Q to decrease, we need our reaction to be overall happening in the backwards direction so that we're reducing the concentrations of our products, which are in the QSP equation. So in which direction will the reaction proceed? It's going to be backwards towards the reactants. And our reactants are our solid, Ag2SO4. Will a precipitate of silver sulfate form? Remember, precipitate just means a solid. And in this question, since the direction's proceeding backwards towards the solid reactants, yes, a precipitate will form. So first we found an expression for the reaction solubility constant QSP. Remember, that works exactly the same as finding an expression for the equilibrium constant in terms of the concentrations of our products. We then calculated the initial concentrations of our two ions in our mixture to find our QSP value. We can then compare Q and K to figure out what's going to happen. If Q is greater than K, the reaction is going to proceed backwards towards the reactants and a precipitate will form. If Q is much less than K, the reaction is going to proceed forwards towards the products and a precipitate will not form.